Good morning, everyone. So we begin the second day with Professor Rajiv Sethi. He will give 2 lectures actually. The first one now and the next one tomorrow. And we plan to continue like yesterday, that we'll have these talks and then discussion in the evening. And whenever we have space, we can squeeze in for some more discussions. So he will be talking today on rationality and complexity in games. Professor Rajiv Sethi.
Yeah, thank you very much. I have the mic. Yeah. Okay, thanks very much. So just please interrupt me at any time during the talk. You don't have to wait until the discussion section. Both the lectures I have just bracketed under the same title. And the first one, which I'll sort of go through very quickly because I think people are familiar with these things already here, so I won't spend much time on it. I just wanted to talk about some of the fundamental concepts and paradoxes in game theory, at least from the perspective of economics. And you may be, certainly you're familiar with the standard solution concepts, but maybe some of the paradoxes may be not fully familiar to you. So I'll quickly go through some of those, and they arise mostly in extensive form games with a sequential structure and a sequence of moves. And then mostly for tomorrow, I'll start today, but finish up tomorrow, talk about some more new research, which is really about alternative solution concepts. I want to suggest to you that Nash equilibrium is not really a universally applicable solution concept for games, that we need others for other contexts, and there are certain situations in which it doesn't work very well, and we need to look for something else. And there are others out there, but there's one particular solution concept called sampling equilibrium that I've been working on recently. It's originally proposed by Osborne and Rubinstein about 20 years ago. But so tomorrow you'll see material that probably, at least I hope, that you haven't seen already. Some of it is not published yet. But for today's talk, some of the things will be very familiar. So if I see people just looking bored, I'll just skip through very fast on that. Okay, but I'd like to start with just an experiment, a simple experiment for which I will just need 10 volunteers. And then we'll collect the data, and then we'll come back to it later. And normally I use index cards for this, but I didn't bring any, so I've got 10 scraps of paper here. I just need 10 people, and I won't tell you what you have to do, except the only thing I'll tell you is that it'll be anonymous. Nobody will know what you write on this piece of paper, and the only thing you're going to write is a number. And nobody will know who wrote what number, right? But we're going to use it to make, to think about certain things later on. I won't even tell you that because it might affect what you do. But without telling, and if you've done it before, no problem, it's fine. Later on I can ask you how it affected your responses if you have seen it before. But I just need 10 people to be willing to write a number onto a piece of paper. Yeah. Can you pass these 2 back there? Thank you. Anybody else? Anand, can you find like 3 people? There's 2 more I need. Okay, can you pass them back there? Just pass it back. Okay, so don't write anything yet. I'll just tell you. Yeah. Okay, good. Okay, very simple. What you have to do is very simple. I'm just going to tell you in a second. I have the clickers. Okay, so you'll see the instructions up here now. So here's what it is. So there are 10 players. So it's an example of a game. All right, there are going to be 10 players. Each person is going to choose a number in the interval 0 to 100 inclusive. You can choose 0, you can choose 100, and you can choose anything in between. Okay? And then we're going to compute the average of the numbers that are chosen by the people over here. We'll cut that average in half. So we'll take half the average. And the person who is closest to half the average will get $1,000. Virtual currency. Academics don't make enough money to run this for real. But just imagine, play it as if it's real, right? Play it as if it's real. You'll get 1,000, and if there are ties, you share it equally, and everybody else will get 0. That's a very simple game, right? So however many people get closest to half the average will share $1,000. That's the payoff, okay? And we'll put this in the structure of game theory later. But you can go ahead and write whatever number you want. Please don't look at what other people are writing, obviously, but just write whatever you want. And then I need one person to help me just collect them. One person who is not writing a number, to just collect them, but fold up the piece of paper so that it's completely anonymous, so that nobody knows what you wrote. Later on, if you want to discuss what you wrote, we can do that. But I just want to collect the data right now. Just tell me when you have 10. You have 10? Yes? Okay, let's just enter the results. Can you tell me, just open one of them at random and tell me the number.
52.
52, okay, next.
75.
75, okay. Now let's stop for a second and let's see what we have so far. We have 52 and 75, and you can see the average here is 6350. I want to reduce the size of this thing so you can see. Can't see this very clearly. All right, let's. Why am I not being able to zoom out? Ah, here, okay.
Use the minus.
Use the minus.
Just control home.
Okay, thank you. Sorry about that. Okay, continue.
58.
58. Okay. So the first person still getting the 1,000. Yeah.
79.
79.
45.
45. Ah, the 45 is now taken over. The 45 is now closest to half the average. It's getting $1,000. Yeah.
0.
0. Okay.
50.
50. Okay. 45 is still winning. Yeah.
Another 50.
Another 50.
25.
Okay.
50 is winning.
25 is winning now.
12. 24.
12. Okay. So the average was 4460. Half the average was 2230. 25 got very close to that. The difference is only 270. And $1,000 goes to individual I, whoever that is, and we don't know and we don't care. But we're going to use this data in a bit, all right? We'll come back to this. And what you saw over here is not that unusual. You know, this has been done lots and lots of times. It's not that unusual, and we want to come back and discuss it later, but not for a while. So let's go back to. Okay, so just forget about this now, we'll come back to it. I just want to go through a few definitions. You're all familiar with it, but so we'll go through quickly. So we're just going to define a game as a set of players. So in this particular case, there were 10 of them, all right, 10 players. Each player a set of strategies. In this case, the set of strategies was just the set of rational numbers between 0 and 100 inclusive. So some countable number of strategies you had in this particular case. A payoff function is a mapping from strategy profile. So a strategy profile is a strategy by each player. So for example, somebody chose 52 out of their set of strategies, somebody else chose 25, etc., etc. You take a profile of strategies, so one strategy for each player, and the payoff function tells you what the payoff is for each player as a function of that strategy profile, right? So it's a mapping from the strategy profiles to the to n real numbers, basically. Okay. In this case, that number will either be 0 or 1,000 or something between the two of them. Now, those are called pure strategies. So I'm going through quickly. You have seen all this before, I'm sure. So pure strategies are deterministic choices, right? The set of strategies that you had. You could also have tossed a coin and, you know, based on whether it's heads or tails, have chosen either 25 or 50 based on the outcome. So that would be a mixed strategy, a randomization of the pure strategies. Now, the pure strategies for a game, and I really want to spend most of this discussion in these two lectures talking about, you know, extensive form games with a sequential structure. And in those games, it's very important to understand that a strategy is a complete contingent plan of action. Once you select a strategy, you should be able to communicate it to another individual or to an algorithm which should be able to implement that strategy no matter what happens in terms of choices by other players without any further intervention from you. So it's a complete contingent plan of action. And if you think about a game like chess, so the strategy in chess has to specify exactly what you're going to do after each board position that can arise. There's more board positions than atoms in the universe, and so the set of strategies in chess is actually much larger than the set of board positions. You have to specify in your strategy not only what you do at each board position, but what you do contingent on how you got to that board position. You might say, oh, that's a crazy strategy. To have a strategy that depends on how you got to the board position is a meaningless strategy, it's not a good strategy. But I'll show you, even in the game you just played, there are strategies that were not good strategies. that doesn't mean that you can just exclude them, right? This is part of thinking about rationality in games. It just tells you what is feasible in the game. So set of strategies can be extremely large. Just keep that in mind. That's the point over here. And mixed strategies are randomizations over pure strategies, so that's larger still, okay? So these are complex objects in most of the encounters that we have faced. The one you saw just now is quite simple, but it itself contains a number of complexities that we're going to come to. Okay. So what's a Nash equilibrium? So very quickly, the formal definition of a Nash equilibrium, the standard solution concept in games, and the main purpose of these talks is going to be really to argue that we need to go beyond this in certain ways. The way that I propose may not be appealing to you, but some other ways have to be found. Okay? So strategy profile, a Nash equilibrium is a strategy profile, so a strategy for each of the players, such that no player can increase their payoff, strictly increase their payoff with a unilateral deviation. So holding constant the strategies that are chosen by the other players, it should not be possible for any one person to choose a different strategy, and by doing so, increase their payoff, right? Strictly increase their payoff. And that's what's written, in the notation up there. And we say that a strategy profile is a strict Nash equilibrium if the inequality here holds strictly. So, if it is, if you're at a strategy profile such that if any player deviates from that unilaterally, they get a strictly lower payoff, right? Not only do they not gain, they actually lose. Then we say that the original strategy profile is a strict Nash equilibrium. And this concept is going to be used a bit in the solution concept that I propose. Chess has an equilibrium, right? It's been known for over a century that it has an equilibrium, Nash equilibrium, but we don't know what it is, right? We don't know whether it secures a win for white, or secures a win for black, or secures a draw for both, right? Intuitively you might think, well, probably either a win for white or secures a draw for both, but we don't know. But it does have a strategy, a Nash equilibrium. So, that's what we know. Most games, we know that it exists. Beyond that, multiplicity, uniqueness, stability, and so on, we know much less. Any idea about Nash equilibrium? I can tell you it exists in the game that you just played. Anyone want to propose? Actually, one person at least knows what it is, based on what they chose, but 0. So if everybody chooses 0, right? The average is 0, half the average is 0, and if anybody deviates, so if somebody deviates even to epsilon, slight deviation, they are going to end up further away from the average than the people who chose 0. So if everybody chooses 0, everybody gets 100, and if one person deviates, they'll move from 100 to 0. It's a strict Nash equilibrium in that sense, right? And the people who remain at 0 will each share 1,000, so they'll get slightly more than 100. So deviating will make you worse off, it'll make the other people better off. Okay? But the key point about why we did this game, actually, it's the first illustration that Nash equilibrium is not necessarily predictive in this situation, right? I can tell you that there's no other Nash equilibrium in this game. It's a unique Nash equilibrium, so it's not a question of multiplicity. But in this situation over here, it's interesting that the closest to 0, the closest to 0 actually is 12, right? And 12 didn't win either. So it's not even approximately a good strategy. So, you might think that a solution concept ought to be prescriptive, that, it should say that, hey, do this, and you're more likely to do better than if you don't do this. It's not a good idea to play 0 in this game. It's simply not. In fact, the person who is closest to 0 is 0, did not win. The next person closest to 0 is 12, did not win. If somebody else had chosen, let's say, 3, 4, 5, 1, 2, would not have won. Right? And you see that the person who actually won 25, chose 25, which is quite some distance from 0. Okay? And that's, in some sense you might say, oh, everybody here except the person who chose 0 is irrational. But that would be a very strange way to use the word irrational. It seems to me that the most rational person is the one who chose 25, not 0. So there's a tension what seems to be what rationality is suggesting, which is Nash equilibrium, and what rationality seems most obviously and intuitively to suggest in this particular game. So we're going to come back to that. Okay? So something else is required to understand. Yeah.
If you are playing this game repeatedly,
yeah.
Then
okay, let's think about playing this game repeatedly. That's a good question, right? If you're playing this game repeatedly, but not here in this room. You all in this room now know that Nash equilibrium is 0. Okay? Now suppose tomorrow you are in this room alone, yourself and a whole bunch of new people who were not in this room with you. Okay? Suppose, for the sake of argument, that those people were in a room just like this. So we had 10 rooms like this. So everybody in all those 10 rooms knew exactly what the Nash equilibrium is. but they did not know that the others knew. They did not know what the others did today. You put those 10 people into a room today, everybody knows what the Nash equilibrium is, they saw it yesterday, okay? Then they choose, is it rational to choose 0?
No, they'll do something like that.
They'll do something similar, and they'll do something similar because, even though everybody knows Nash equilibrium is 0, they don't know that everybody knows. And more importantly, they don't know that everybody knows, and so on, up the hierarchy of beliefs. So this is, just knowing that the Nash equilibrium is 0 is insufficient for it to be prescriptive. So then you might say, okay, repeat it 3 times. But again, unless you have very strong assumptions about common knowledge, that people, everybody knows that everybody knows that everybody knows, all the way up to the hierarchy of beliefs, it's not clear that Nash equilibrium is even prescriptive, that it's a good idea in this particular situation. So we'll come back to this and say, there are people who have developed models of reasoning that are more accurate in terms of their prescriptive results, and we'll come and see some of these things, all right? But first I want to just go through and talk about a couple of other things. So let's save this just in case we want to come back to it. Okay, so we see that there's an equilibrium, but we also see that the equilibrium is not prescriptive in this case, and I hope I've convinced you that repeating it is not going to be enough. In fact, if you imagine changing the payoffs a little bit, so that if you're below half the average, you've got to pay me $1,000, right? Nash equilibrium is still 0, right? But now, you might get even higher numbers that people are reporting. But just think about that, yeah.
Just could I see something like this, that people's brain are just, I wouldn't say stupid, I would say tired to think iteratively more and more and scan through all the beliefs. Suppose that I replaced people with 10 computers, given them this thing and some logic, would they have reached 0? Because it seems to me if I
so think about that for a second. That's a really good question. Think about that for a second. Suppose that you had computers that were themselves learning, right? So that they had different ways of playing this game. So you gave them the game. There's some procedure that's being adopted. Each one is a different algorithm produces this. How would the learning process? Where would it drive them? In this particular case, the person who chose 12 sees that they chose too low. Even though they chose too high relative to Nash equilibrium, as far as the winner compared to what they chose too low. Reinforcement learning or any kind of learning process will tend to push that person upwards. You're right that some people will be pushed downwards, but also some people who are close to 0 will be pushed upwards. Where that process ends depends on the specifics of the dynamics. Yes, I can write down dynamic processes that will converge in a limit to 0. Yes, but of course I can also change the payoffs in such a way that 0 is penalized while remaining a Nash equilibrium and make that process much harder. But there are other dynamic processes which will not converge to 0. And I'll give you a reference for a paper that looks at some of these issues. So we'll come back to that. Okay, so let's very quickly, just this game I want to use quite a bit because it's a very simple game actually in some ways. Nash equilibrium is extremely simple in this situation, and it's one of the cases where people say, it's obvious that people will play Nash equilibrium, but I want to even challenge that in this particular case. So you have 2 players, one chooses rows, high, medium, low, and one chooses column, high, medium, low, okay? And the payoffs, I'm sure you're familiar with this. The first number is the payoff to the row player. The second number is the payoff to the column player. Okay. So if they both choose high, they both get 6. If the row player chooses medium and the column player chooses low, then the row player will get 1, column player will get 5. Okay. Nash equilibrium. LL, yeah. Nash equilibrium, remember, it's a strategy profile, not a payoff profile. But yes, it generates a payoff profile of 2, 2. Yeah. So both choosing low, because you can see that no matter what if the column player chooses H, my best response is low. I get 8 by choosing low. If they choose M, low is best. If they choose low is still best. It's a dominant strategy. So in fact, not only is this Nash equilibrium, it's a dominant strategy equilibrium. Okay. So just keep this in mind. We want to come back and think about whether Nash equilibrium, even in this case. Now, of course, it's inefficient if the players could collude, if they could write a contract, if they could persuade each other, communicate, maybe they'll move to something better for both of them. But unilateral deviation will hurt.
Pareto optimal state is
Pareto optimal will be, both choosing high, correct, but even both choosing medium will dominate choosing low, that is correct. But in order to achieve 4 for each player or 6 for each player, you need a coordinated deviation. Unilateral deviation cannot do it, right? You need both players to deviate jointly. Any unilateral deviation from low is going to hurt you. Okay, as long as the other person chooses low, if you deviate, you're gonna get hurt, right? So it's Nash's dominant strategy. Seems like obvious what the answer is over here, but let's think. Let's come back to that also. All right. Okay, let's take one more example and then we'll go through. So this is an all-pay auction, and you know, when we normally think, when non-economists especially think about auctions, the idea of an all-pay auction is a bit strange. So what's an all-pay auction? It's very similar to a regular auction. Everybody places a bid. Think of a bid placed in an envelope. It's not an open outcry auction. It's a sealed bid auction. You write down your bid and you send it off to the auctioneer. And the winner of the auction is the one who submits the highest bid. If 2 people submit, this is a 2-player game I'm going to show you. If 2 people submit the same bid, they each get the object with a 50% probability. So the ties are broken uniformly, okay? What happens if you lose? If you are outbid, or if you tie and the tie break goes against you, right? Then you don't get the object. You still have to pay. That's what the all pay means. Okay, so an all pay auction is one in which even the loser has to pay. Is that clear? That's just the rules of a game. You might say, well, what kind of auction is this? Who's going to participate? All pay auctions are more important economically than the regular auctions. Regular auctions are important for art, for wine, for spectrum auctions in the United States, for instance, for all kinds of things. But all pay auctions, just think about it. 2 firms, let's say Merck and Pfizer, who are trying to develop a new drug, right? One of them is going to get it first, and they'll patent it, and the other person's investment is wasted. That's an all-pay auction. You are both investing resources, right? And one of them who gets there first will get the full price of the patent for 19 years in the US, and the other person will not recover their investment. Lobbying is an all-pay auction, right? Where one person wants a law to go in one direction, another person another direction. They both try to bribe, or bribery is an all-pay auction. They both try to bribe the politicians. Somebody wins, somebody loses. You don't get your bribe back, right? Similar with lobbying, which is sort of weak form of bribery, I guess. Depending on your perspective. And you can think about other kinds. In fact, yesterday, when you talked about arms races and war, there also, you have this similar kind of feature. So it's economically important. So let's take a example. Take an object with a value of 5/2, all right? 2 bidders, simultaneous bids, non-negative integers. So they can only bid 0, 1, 2. It doesn't make sense to bid more than 2 because the object is worth 2.5, right? So you don't want to bid more than 2. And the ties are broken at random. Okay, here are the payoffs. So, just see how the payoffs are determined. If both the bidders bid 0, right, then the winning bid is 0, ties are broken at random. So each person gets a 5/2 object with 50% chance, and that's where the 5/4 is coming from. Okay, that's the thing. If one person bids 0 and the other person bids 1, then the person who bids 1 wins the object. So their payoff is 3/2. Why is it 3/2? Because they get 5/2 minus what they pay, 1. This person bids 0, so they pay nothing. If this person bids 1, this one bids 2, you will lose your 1 because you don't get the object. The other person will get 1/2 because they get 5/2 minus their bid, which is 2. Okay, so those are the payoffs over here. Any Nash equilibrium? So actually the best response to 0 is 1. If you know the other person is going to bid 0, the best response to 0 is 1, best response to 1 is 2, best response to 2 is 0. 1, 1 is not a Nash equilibrium because if you have 1, 1, if both people are bidding 1, I would rather change to 2. Instead of 1/4, I will get 1/2, right? Because instead of getting the object with 50% chance, I can get it with 100% chance. So there's no Nash equilibrium in pure strategies, right? But in mixed strategies, there has to be. This is in Nash's theorem. So pure strategy equilibrium does not exist. So very quickly, this is really what we mean by Nash's theorem. Nash's existence theorem is that every game, under certain conditions, right, which includes just about anything that you can write down in an applied setting, has a Nash equilibrium. And basically, the conditions are, if the strategies of the players are compact and convex subset of Euclidean space, and the payoff function is a continuous function, then equilibrium exists. These are very easily satisfied. And the reason why the strategies have to be, compact and convex subsets of Euclidean space is if you allow for mixed strategies. Mixed strategies are just, they're just, in the unit interval to the power of however many strategies there are, right? It's in the unit simplex. So it's once you allow for mixed strategies, there has to be Nash equilibrium in any finite game. This is really basically Nash's result. Okay, as long as the payoff function is continuous. Okay, and the proof of this thing, the way he did it, actually, it's a 2-page paper. It's I just like to tell people about it because the paper contains almost no notation. It's entirely in words, right? He uses words like this: complex, convex, compact subset, etc. And it's an application of Kakutani's fixed point theorem, which was proved a few years before Nash. And basically, he just showed that if you have a finite game, you allow for mixed strategies, you satisfy the conditions of the theorem. So the heavy lifting was done by Kakutani. Nash just appealed to that. It's a 2-page paper. And the implication is that every finite game has a mixed strategy equilibrium. So, sorry, forget about this because I removed some slides for this, but I'm just going to go straight to this one, the all-pay auction. We know that it has a Nash equilibrium by Nash's theorem, and if you can compute it, it gives 1/5 probability to the 2 extreme bids and 3/5 to the middle. And if you assume that the other player, the column player, is choosing in these proportions, then the row player becomes indifferent between all the 3 bids, and therefore can also and would satisfy the Nash equilibrium condition that no unilateral deviation will pay. Okay, it's not a strict Nash equilibrium, but it's a Nash equilibrium. And if you calculate the equilibrium payoffs, they are 1/4 to each player, because there'll be situations where they tie, there'll be situations in which one player loses and pays a positive bid. And if they collude to pay, just to bid 0, both of them, they can get 5/4. So it's inefficient in the same way as you saw with that other game, but in a slightly more subtle way. Okay. Okay. In case you're interested in the proof, I've got this YouTube playlist that I did for Columbia grad students, first year PhD doing the math methods course. And there's one thing which this is from Nash. This is exactly how he wrote the paper. In text like that. It's 2 pages, so it's worth looking at if you like. And if you're interested, you can go through this video. It just goes through line by line this or para by para Nash's argument. Okay, so let's talk about paradoxes, and then we'll sort of set up the stage for alternative solution concepts, most of which I'll discuss tomorrow. Okay, so the next step after Nash was Selton. So if you recall, the Nobel Memorial Prize in Economics was shared by Nash, Selton, and Harsanyi. So Selton's contribution was to look at games with a sequential structure and say that there are some Nash equilibria that don't make sense in this setting. So let's refine the set of Nash equilibria through what has come to be called subgame perfection, right? So here's Selton's examples. This is all taken from his paper. This was in 1965 in a German publication, Zeitschrift für die gesamte Staatswissenschaft, which I've just cut and pasted from over here, right? So this is, except for this thing which I wrote, but this one is Selton's own example. So you have player 1, so this is, it's a 2-player game, but there's a sequence of moves. So player 1 can choose either to move to the right or to the left. If player 1 moves to the right, then player 2 is not called upon to move at all, okay? And the payoffs are 2 and 2 to each player. Player 1 moves left, then player 2 then is called upon to move, right? So then player 2 knows that player 1 has moved left, and player 2 can move right or left, and if player 2 moves right, the payoffs are 0-0, and here the payoffs are 1-1. Now if you express this in this form, if you just write it, because each player can move left or right, okay? And you remember, the strategy has to give you a complete contingent plan of action. So even player 2 has to specify whether they'll move left or right if they're called upon to move when they specify their strategy, even if it might turn out to be the case that they're not called upon to move, right? So we can write it in this form. So think of player 1 over here. Player 1 can move left or right. If player 1 moves to the right, then the outcome is 2-2, no matter what player 2 chooses, because player 2 is actually not called upon to move. But if player 1 moves left, then it matters. If player 1 moves left and player 2 also moves left, then the payoff is 3 to player 1, 1 to player 2, otherwise 0-0, which is coming from here. Okay, so that's just the bimatrix form representation of these payoffs over here. Okay. Now Selton's argument was, look, for them both to move left, for them both to move right, player 1 moves right, player 2 moves right. So look at this situation over here. This is actually a Nash equilibrium. It satisfies the Nash equilibrium condition. And Selton said, well, we can ignore that because it's not reasonable. Why is it not reasonable? because even though you have two Nash equilibria here, this is a Nash equilibrium, both playing right, left is also a Nash equilibrium. He argued that player 1 can reason as follows: if I were to move left, right, then player 2 would basically be faced with a choice of 1 or 0. They would choose 1 because they prefer 1 to 0. Therefore, I can assume that they will choose left, which means I will get 3, whereas if I move right, I will get 2, so let me move left, right? It doesn't make sense for me to move right. I can assume that player 2 will do the rational thing and move to the left, so I should knock out this equilibrium. It doesn't make any sense. Okay. Now, okay, that sounds very reasonable. So this concept is very widely used, obviously, right? In fact, the standard way of approaching a game with a finite number of moves. But Selton himself then in 1978 paper said, no, wait, there's something wrong with this reasoning, right? And this is how he explained it through what's come to be called through what he himself called the chain store paradox. So chain store paradox is a very similar game. So think about this. So the idea of the chain store paradox is that he said, imagine a chain store which has branches in multiple cities, and you have in each city a local entrant, a local competitor who can either open a store and compete or not compete. So think about one particular town. So first the local competitor decides in or out. In means that they're going to compete. If they compete, the chain store here is player A, can either aggressively slash prices, right? In which case they are both hurt. Both the chain store and the local competitor are hurt. Or they can accommodate. So they can either be cooperative or accommodating, or they can be aggressive. If the chain store is aggressive, they both get 0. If the chain store is accommodating, they both get 2, right? But the best thing for the chain store is that this person just stays out, right? If they stay out, they get 1, and the chain store gets 5 in this particular town, okay? Now, if you apply the same reasoning of the subgame perfection and assume that there's 20 different towns, well, after 19 town decisions have been made, no matter what the decisions have been made, you come to the 20th town, this is what you're faced with in the 20th town, right? Apply the chain store reasoning, the subgame perfection reasoning, and the entrant will say, okay, if I do this, if I come in, then the chain store will cooperate because they prefer 2 to 0, and so therefore I should enter, no matter what has happened before, I should enter, because I will get 2 instead of getting 1. And if they enter in the last period, the chain store should accommodate. That's the reasoning. But Selton said, wait, think about this for a second. Then you can apply this reasoning to, you have applied it to the 20th town, now apply to the 19th, to the 18th, you know what's going to happen, so you can, so in every town the entrant will come in and be accommodated. But he said there's something non-intuitive about this. In the first town, if the chain store comes in and says, and just, behaves aggressively, suddenly it's done something that equilibrium says you should not be doing. At that point, everything's out the window. How should then the entrant in the next town react? The first entrant should not have been punished by aggression, but was, and therefore, that suddenly creates a bit of a paradox for the second town, because what was not supposed to happen if everybody had followed the equilibrium reasoning actually happened, right? And he argued that intuitively the chain store might want to fight entrant in the first town or the second town or the third town, maybe to establish a reputation for being non-rational, for being, for not having the payoffs that everybody thinks it has, willing to lose money just to punish certain types of behavior, etc. By doing so, paradoxically, it may be rational in the sense that it will deter entry in subsequent periods, and it will end up with overall more money than it would have if it had followed the prescriptions of the equilibrium strategy. Okay? All right. And this is just what happens in 2 periods. It starts to get a bit complicated, not quite as complicated as the game yesterday that you put up, but once you put in 20 periods, you're going to have pretty convoluted game tree. This one is a beautiful example from Bob Rosenthal. If you're familiar with this, I'm sorry, you're going to be bored, but very soon you'll get to something new. Okay. This is referred to as the Centipede Game, and here basically, each player can either choose down or across, and if you move across, then the other player is called upon to move down or across, and so on, all the way to the end. If you go all the way to the end, they each get 10, right? But if you reach the end, player 2 can get 11 by moving down over here, okay, rather than 10. So if one assumes that 2 is going to move down over here, then 1 over here can get 8 rather than 7 by moving down. And you can apply this reasoning all the way back, and the only Nash equilibrium actually, forget about subgame perfection, the only Nash equilibrium in this game involves player 1 moving down right at the beginning. And if you imagine this not only stopping after 10 periods, but after 100 or 1,000, you're leaving a lot of money on the table. And that's itself unintuitive. That, it might make sense for player one to move across just to see, well, what the hell happens, because maybe the game will continue and we'll end up with much, much better payoffs at the end, right? So that's in some sense also a paradox. And in that case, you don't even have to use subgame perfection. Actually, it's the only Nash equilibrium of this game. Okay, this is the data from the game you played, which is referred to sometimes as a beauty contest game or a guessing game. So you're really guessing what the other players are going to write down on the piece of paper that you did. And this is classic experiments by Rosemary Nagel, who showed first that you get this pattern of behavior. So this is not too far from what we saw, although the numbers in this room were somewhat higher than you see in the Nagel's data. But basically what she observed is that you spread across the entire interval, but you get certain spikes. And because you get certain spikes, you can start thinking about a possible theory to try to explain these spikes. So here you've got a spike at 50, for example. You've got a spike at 25, 12 and a half. You're getting these spikes at intervals that seem systematic. And that sort of suggested that there should be another approach to try to think about how people reason in a game like this. An approach that leads you somewhere other than Nash equilibrium, that leads you to something like this, okay? All right, good. So, good. So I've sort of breezed through that stuff because, it will be familiar to most of you, and I didn't want to spend too much time on things that are well known and are in textbooks. So let me move now to what I had planned for the second lecture, but I've got plenty of stuff to talk about, so I'm going to start now. But I'll pause for a second if there's anything about this. So what I've given you so far is completely textbook material. And now I would like to move towards something that is actually at the other extreme, which is sort of kind of, very quickly I'll move on to something that's kind of speculative and you may find unintuitive or unappealing. We'll see. Yeah.
Just from an application perspective.
Yeah.
So assuming that you have a huge dynamic game, and as
Yeah.
you said, you can study what you have said is open loop more or less versus closed loop, right?
Yes.
And
Yes.
you say open loop is not rational and closed loop will be smarter and so on. But how do you select? Basically, people can reason in both ways, perhaps with a tree or perhaps with like just this matrix games that you saw. So of course, for two iteration, for two time step, it's okay.
Yeah.
Assuming that you have anti-step.
Yeah.
Step, you can completely imagine that people will just look at the matrices, then just solve backward reduction. So how for an application you should choose, or what would be a procedure between?
Yeah. Well, the second part of my talk, which I'm going to start in a second, is exactly about that question, which is about procedural rationality, actually. So, but I'm going to move quite far away from the kind of reasoning that's used to motivate the solution concepts, the standard solution concepts. So one of the things that I'll go through, which is exactly what I'm working on right now, is to treat it actually as a sort of a bandit problem. So basically, you have a set of actions. You really don't know what those actions are what's going to be the result of those.
Algorithm and see.
Let me get to that. Yeah, let me get to that. But actually, that's exactly the question that I want to deal with. But it'll be quite a departure. Rather than using what the standard model as a starting point, we'll start somewhere totally different. But let's see where we go. Any other questions or comments about this? Okay, so just to repeat, what you've seen so far is just textbook stuff. Okay, you probably knew it already. I hope you weren't too bored with it. Okay, so let's first talk about the models that emerged in the light of Rosemary Nagel's beauty contest experiment. So these are the so-called level K models. We saw that in the half the average game there's a Nash equilibrium, but you also get this distribution of data. The data that comes out of the experiments looks very different. So let's see if we can try to think about how this might work. So level K models, and I won't spend much time on it because this is not my own research. And again, this is quite familiar to, what's that?
I'm scared of asking this question.
Please ask.
Once I saw that, I would think, let's say I don't know anything about Nash equilibrium.
Yeah.
I play this game.
Yeah.
And I would assume that if I tell people that choose a number between 0 and 100, I would assume they'll all choose randomly between 0 and 100.
Yeah.
And obviously the average, statistical average would be 50.
Yeah.
Half the average will be 25.
Yes.
But that is only when you are not telling people that I'm going to reward you on the half the average.
But I told you that I'll reward you half the average.
That's the point. But otherwise, 25 seems to be the normal.
What you just described, Somdatta, is exactly what in the level K model is referred to as level 1 reasoning. Level 1 reasoning, level 0 reasoning is exactly choosing randomly, right? In the interval 0 to 100. Level 1 reasoning says, wait a second, I'm about to choose randomly, but wait, let me not. What if everybody chose randomly? If everybody chose randomly, the average would be 50, roughly speaking. Half the average would be 25, let me pick 25. Somebody who picked 25 in the data was actually, possibly, who knows? Who knows what they were reasoning? That could itself have been just a random number, or it could have reflected your reasoning with 25. But why stop there? Somebody might say, look, if everybody chose 0, randomly, it would be 50. But maybe everybody's figured out that randomly it would be 50. And so they're going to choose 25. If everybody's going to choose 25, I should choose 12 and a half. That's what she's seeing over here. She's seeing 25, but she's also seeing spike at 12 and a half. And one could go further and say, oh, maybe people have figured out that if everybody chooses randomly, I should choose 25. So they're going to choose 25. But maybe they figured out that no, that other people have figured out that they should choose 25, so therefore they'll choose 12 and a half. And maybe I should therefore choose 6 and whatever. And you see some people doing that too. So these spikes are not randomly distributed, right? Nor do you get random plus 25, which is where you would get if everybody stopped at level 1. So the level K model basically just formalizes this intuition, systematizes it a little bit more. Level 0 players choose uniformly. Level K players choose based on the belief that others are level K minus 1. And the distribution of types implies the distribution of strategies. So, in any group, there will be different people, who reason partly because they're tired, they slept well or didn't sleep well, or because they're bothered or not bothered, depends, will reach a different, what I call depth of reasoning. But that, the distribution of the depth of reasoning will give you the distribution in the population, in the group of experimental subjects. And that's a very different approach than Nash equilibrium.
In this experiment,
yeah.
they are playing this game only for one time, right?
Yes. Yes.
Suppose these players, after looking at the results,
yes.
are allowed to play like multiple times, then it may converge to 0. Like
it certainly may converge to 0, but you certainly don't want to converge to 0 too fast. I mean, imagine you play it the second time, right? For you to then confidently pick 0, you need to really be convinced that other people are going to assume that you are going to pick 0. They need to have a lot of confidence in your having decided that they're going through a whole iterative chain of reasoning in one step. So if you're a little suspicious about that, you might decide, okay, let me pick 1 or 2, or maybe even higher. But yeah, the average distribution should fall over time. It should fall over time. Unless I change the payoffs and say, look, if you're below half the average, you've got to pay me. Then it changes a bit. But these are things, I'll give you a reference for looking at these two cases a bit later. Okay.
I have a question. Can you go back to your graph that you showed for the experiment?
This one? Yeah. This is just taken from her paper. Yeah.
No, I know. So the peaks at other positions different from 25 and so say at 12 and a half. I mean, how do you know that the way you are explaining the n-tuple reasoning, that is the explanation for these peaks and not something else?
Good. So you don't. For this particular experiment, you don't. But what you have to do then is to take that model and apply it to other experiments. Right. Get the prediction for those experiments and then compare it to the outputs. And actually, there's a book by Colin Kammerer, Behavioral Game Theory, where he argues that many experiments in which we thought were successes for Nash equilibrium. By the way, I don't want to be taken to suggest that Nash equilibrium is not a useful concept. It's immensely useful and it's very, very applicable in a wide range of situations, but there are important cases in which it doesn't apply. And I want to fill that space, or try to fill the space in which it doesn't seem to work so well. This is the case in which it doesn't seem to work so well. Kammerer makes the argument that there are situations in which Nash seems to work so well But if you carry out this reasoning, level 0, level 1, and I'll give you a couple of examples in a second, you will end up with something that gives you the same prediction as Nash. And that is really your point, is how do you know? How do you know it's Nash? Previously we thought it was Nash because that was really the standard solution concept. But it could even be coming out of this, or something else entirely. Right. So the only way really is to see how versatile the concept is, to try to figure out, well, what does it predict in this environment versus that versus a third environment? And ultimately you tentatively settle on what explains the data best. But if somebody comes along with a better theory, you have to stand ready to reject the solution concept. Yeah.
I mean, I was just wondering that this is a very mathematical form of reasoning, but people usually use heuristics.
Yeah, that's what I want to get to. Yes, I want to get to a different approach. Yeah, and then I like to get your feedback because I'm working on it right now. Yeah. Okay. Yeah.
What you have been talking about till now, that you take half of that half and the way that math side. Isn't that a very it's like a mathematical thing that okay, we take half and then half of that and then half of that and then continue on. And when you have to choose a number, say okay, I've chosen a number, you have to tell me what number, that particular game again, you always being mathematically. But if you had, in this case, the numbers that you had from us, you had one major shock number or a couple of shock numbers which are so below that brought down the average, right? So if you have those shocks, is it possible, I'm just talking from the application perspective, if you have everything going that way, in one particular, if all the numbers initially were the higher numbers, right? And then you have a major shock being put in, which brings down the average. Yeah. Then that's in your favor. Is it possible to insert shocks when you think that it's going to happen, or can shocks be predicted? Well,
what you're calling a shock is actually a choice that is closer to the Nash equilibrium prescription, right? What you're calling a low number,
I'm saying that the idea was that if you know that this is a way that everyone is going, suppose I know that everyone is going to pick the higher number, and I know that the average will come down to somewhere say 50 or early 40s. So I'm going to choose a number that is so low that it brings a shock to the system that even they don't know. That surprise factor, how costly would that be? How costly would it be to insert a shock?
In terms of the payoffs of this particular game, the cost is simply that you don't win, right? But somebody's going to win. Somebody's going to win, because it's not, the way this payoffs are set up. All you do is you might shift the winner slightly lower. Somebody, you might shift the winner from somebody who said 32 to somebody who said 25. Yeah, that's what's going to happen. But it's not going to, if your estimate of half the average is, let's say, 17, which comes up quite often, and you deliberately say 2 or 3 or 1 or 0, your chances of winning are going to go down, at least even based on your own estimation of the distribution of numbers. But you will shift, that's right, you will shift, you'll change who the winner happens to be in all likelihood. Yeah. But maybe I'm not fully understanding your question, but let's come back to it. Okay, so we have about 12 minutes left for today, so I'm just going to go into what I had planned to talk about tomorrow. Okay, so let's think about level K equilibrium in this game. So I really want to come back to this game a few times today and tomorrow. Remember, this is what we looked at before, right? This is sometimes called a public goods game. It's a 3-person prisoner's dilemma game. It's a very simple game actually, but it has some very surprising properties that I hope I can convince you of. But let's first look at what's level K, and I want to argue level K doesn't work too well over here, right? For this thing. So, what would level K tell you for this particular game? Level 0 we know, right? Level 0 is just choosing randomly, all three. They choose high, medium, low randomly. So level 0 will choose, roughly speaking, 1/3, 1/3, 1/3 probabilities for each of these 3 actions. But what does level 1 do then?
I just assume that the others are doing that and I try to optimize it.
Yeah, so what would that optimization?
Just compute my best reply is I compute my expectation.
But what is the best reply in this game?
One third, and then optimize which one is the best.
But there's a dominant strategy here. The solution is right in front of you.
H.
If my opponent is choosing HML with probability 1/3, 1/3, 1/3, what should I therefore do if I'm the role player? L. No matter what they choose, L is dominant strategy. Even if whether it's 1/3, 1/3, 1/3, half, 0, half, it doesn't matter what they're choosing. L is a dominant strategy. I actually don't care what they're choosing. It's still always the best prize always to choose L. It's a dominant strategy. So the level K model here says level 0 plays uniformly across these strategies. Level 1 will choose L with 100% probability. Correct? What about level 2? Level 2 assumes that others are level 1. Would be best reply to L?
H. No.
L again. So, this predicts that all the levels are going to choose L. So really, basically the Nash equilibrium, right? Basically just the Nash equilibrium, except for the level 1. So the level K model in this particular case predicts Nash equilibrium with noise. Depending on how many level, if everybody is level 0, it'll just be a uniform distribution of these actions. If a small number of people are level 0, you'll just see the Nash equilibrium with a bit of perturbation. So it's predicting something that's testable, right? But is not actually very consistent with the experimental data. I'll show you that later. But the prediction can be calculated. The prediction is simply, you'll have uniform of the actions, but then a big spike at the Nash, right? Okay, so we know what the model predicts. Now I want to give you a completely different approach to thinking about procedural rationality, exactly the question that you asked, right? Which will give you a very different prediction in this, and I want to claim that is empirically more valid. Okay, and this is what I'll refer to as sampling equilibrium. So the original introduction of this was in a paper by Martin Osborne and Ariel Rubinstein in 1998. And they called it a slightly different name. They called it, SK equilibrium, but I will just call it sampling equilibrium. You'll see why. Okay, let's take a symmetric two-player game with M pure strategies. So the one you saw, the example you just saw is a symmetric two-player game with 3 pure strategies, right? So M is 3. Okay, but we take any. Okay, let P denote an arbitrary mixed strategy. Right, so any distribution, so 1/3, 1/3, 1/3 would qualify, but take any arbitrary mixed strategy for this game. Now, I'm just going to give you a story to motivate this concept, but the concept is independent of the story. So imagine a large population, and people are playing these actions. There are M different actions, and people are picking these with the probability P1, P2, P3 all the way up to Pm, right? So this is a distribution, there's a frequency distribution in a population over the choice of actions that people are taking, and people are just mechanically choosing one of these actions whenever they're called upon to play this game. Okay, imagine that I enter this population. And I want to figure out what to do. All I know is that I have these actions. I don't really know that I'm playing a game even, right? How should I decide what action to take? The sampling equilibrium approach basically says, okay, let's try each action, right? In the simplest case, let's try each action once and look at the payoff that I get. Whichever payoff I get, whichever action leads me to have the best realized payoff, I choose that action and I enter the population. And you can think about this process, this dynamic process, where some people are leaving the population and people who are entering sample each action, they look at which one got the best highest payoff, and then they enter the population.
And once they enter, do they continue to update?
They can, no, just for the sake of argument, for the sake of the story, assume that they just stick to their action, and then they exit and new people come in. But you can also tell this story, you can also do this with a population that is fixed, where people are randomly called upon to update, they sample and then they update. So this.
You don't have memory. This thing that a new guy is coming in means that he's not remembering
A new guy is coming in is genuinely new in the story that I told you. Yeah.
So you don't have memories.
No, you don't have. And the alternative story, which I can give you a reference to a paper that works this out, which gives you exactly the same dynamics, is a population that is fixed, no entry or exit, but people are called upon to, given opportunities to revise the action. So they're taking an action, then occasionally they try to think, oh, am I doing the right thing? They sample each action once, they pick the one with the highest payoff, and if it's different from the one they were taking, they switch. So this story gives you exactly the same dynamics, but they're equivalent. So stick with whichever one you prefer. But now think about a steady state of these dynamics, right? Now, as a steady state of this dynamic, whenever somebody comes and they sample each action, right, the likelihood that the first action will win the sampling procedure should be precisely equal to the likelihood with which it's being played in the incumbent population. So let me just repeat that. That's the key thing about sampling equilibrium. Sampling equilibrium is a frequency distribution over actions. So the first action maybe is played by 20%, 30%, 50%. Imagine that, all right? That is actually very close to sampling equilibrium in the game that I showed you. So 20% high, 30% medium, 50% low. Imagine this is the frequency distribution in the population.
Are you talking about frequency-dependent payoffs?
No. No, I'm not actually talking about payoffs. I'm talking about probabilities of securing the highest payoff. It's an order statistic. So if I go back to this thing, suppose that I have got 20%, 30%, 50% in the population playing high, medium, low. I choose high, right? There's some probability that I'll win. There's some probability that I'll choose high, medium, low, and I'll record my payoffs. Each time I choose this action, I play against an independent draw from that population. That draw could be playing high, medium, or low, because there's 20% high, 30% medium, 50% low.
Depend on the frequency.
Yes. The likelihood that high will result in the highest payoff is certainly frequency dependent. But the reason I didn't want to call it frequency dependent payoffs, it's frequency dependent winning probabilities, if you like. Right? The likelihood that high will win my sampling procedure is frequency dependent, yes. Right? But I'm not focusing on, the word frequency dependent payoff is used in evolutionary game theory in a particular way. I was trying to avoid that because evolutionary game theory gives you completely different predictions in this. Evolutionary game theory, if it converges to anything, if evolutionary game dynamics it converges to Nash. And I want to give you a dynamic that. Okay. All right. So basically what is a sampling equilibrium? Sampling equilibrium is defined as follows. So let P be the probability, the frequency with which each action is being played in the population, and let Wi of P be the likelihood that action I results in the highest payoff when you sample every action once. Okay, that's the definition of WIP. It's a random variable. And yes, it does depend on P. Right? A sampling equilibrium by definition is a mixed strategy P star, such that the likelihood that action I will turn out to be the best action, the probability with which it turns out to yield the highest payoff under sampling is precisely equal to the likelihood with which it is being played in the incumbent population. That is the definition of a sampling equilibrium. Okay? Yeah. WI is the probability that action I results in the highest payoff when you sample each action once.
Out of P to P, P1 to P.
1 to M. Actions 1 to M, you sample each of the actions 1 to M once. Every time you sample, your opponent is choosing an action with the probability distribution P. So you're picking a randomly drawn opponent from a population with frequencies P. There's going to be some chance that H wins. There'll be some chance that M wins. There'll be some chance that L wins. All of these things can win. You can see H will win, for example, if when I sample H, my opponent plays H. When I sample M, the opponent plays M or L. When I sample L, the opponent plays M or L. In that case, H will win.
What is the link with ontology and logic? Because if you take a logic in this case,
yeah,
you will approximate this function when
yes,
ontology is going
yes,
to infinity
Yes, in fact, qualitatively, sampling equilibrium gives you predictions in games that look like quantum response equilibrium. But here's the important difference. Sampling equilibrium, like Nash equilibrium, is parameter free. Quantum response equilibrium has a one tunable parameter. And if you want to get close to sampling equilibrium with QRE, you need to tune that parameter exactly right. Okay? And my claim actually is that sampling equilibrium will give you a good fit to the data in multiple experiments, parameter free. If you try to get the same fit with quantum response, you'll have to tune the parameter to be very high in some games and very low in others. You cannot do it with a single.
But this parameter also can help you to know the certainty of, let's say, of your model, right? So you can.
Yeah, the parameter has an interpretation. Yeah, but oh, am I out of time?
No, I think you have 10 minutes.
I have 10 minutes more.
Yeah.
10 minutes for discussion. I'll try to reach a place which is a natural stopping point, then we can continue tomorrow. Yeah. Okay, so at least we know what is, I want to show you something very surprising about sampling equilibrium, and then we'll talk about, what I'm working on right now is sampling equilibrium in repeated games, which I'll talk about tomorrow. But I want to show you something very surprising here about just in this particular game. So we all see the definition of sampling equilibrium, okay? Now the first thing to notice is that every strict Nash equilibrium must be a sampling equilibrium. So let's see why. So we know that this is LL is a strict Nash equilibrium, right? If I deviate from L, I lose. If I deviate here, I get 1, here 0, so I strictly lose. So LL, which yields this payoff 2, is a strict Nash equilibrium. There has to be a sampling equilibrium where the probability distribution P is 0, 0, 1. Has to be. Why? Because if the population is 0, 0, 1, then when I sample H, my opponent will play L with probability 1. Right? I'm picking some with probability 1. Same here, same here. So in this case, my payoff will be 0. In this case, my payoff will be 1. In this case, my payoff will be 2. So the probability with which L will win is in fact 1, which is exactly the probability with which it is being played in the population. So that has to be sampling equilibrium. And you can easily see that any strict Nash equilibrium must be a sampling equilibrium. So it seems as if sampling equilibrium is not giving us anything. You know, it's just reproducing. You know, whenever you have a strict Nash equilibrium, it must be within the set of sampling equilibrium. It appears as if the concept is a bit of a waste of time, and I want to show you that it is not. But it appears as if it is not, because it's just using the strict Nash equilibrium, it's just generating strict Nash equilibrium whenever it exists, it gives it back to you. Okay? Okay, now okay, I'm going to skip through the auctions, we don't care. Okay. So, what I just explained to you is that P is 0, 0, 1 is in fact a sampling equilibrium. Okay? However, here's another sampling equilibrium. Alright? And it takes a little bit of work to verify it, but trust me, it is a sampling equilibrium. There's a sampling equilibrium where H is chosen with about 20% chance, L with 28%, and H with 52. These are not exact, these are rounded numbers. The exact, you know, is irrational. What does this mean? That means that if the population is playing this with 20%, 28, 52, and I come and sample these three actions, there will be a 20% chance that H will give me the highest payoff. And 28% chance that this will give me the highest payoff. And 52% chance that this will give me the highest payoff. Right? So, in addition to the strict Nash equilibrium, there exists, at least, in fact in this game, there exists exactly one more sampling equilibrium. Now this example was in the original Osborne-Rubinstein paper in 1998, American Economic Review. And I saw it when Ariel Rubinstein presented it. I'm going to stop and just, yeah.
I missed the second champion.
How do you compute this? So you take P1, P2, P3, and then W1, W2, W3 are functions of P1, P2, P3. These are going to be polynomials, and you find fixed point. That's how you compute it. But it's not trivial. Yeah, you have to solve this, the set of nonlinear equations, Wi of P equals Pi for each I. Yeah. Okay. So when I first saw this, I was convinced So this example is in the Osborne-Rubinstein paper. When I first saw this, I was convinced that if you actually write down the dynamics that I showed you, that I used to motivate, the story that I used to motivate the sampling equilibrium. So remember, Wi is the likelihood that action I will win the sampling procedure, and Pi is the probability with which it is being played in the incumbent population. So if we write down the dynamics should say something like, if Wi is bigger than Pi, then Pi should increase. If Wi is less than Pi, then Pi should decrease. Right? If an action wins the sampling procedure with higher frequency, with higher probability than it is being played, it should become more prevalent in the population. That's the sampling dynamics that motivates the whole concept. And I was convinced that if you write down these dynamics and you look at stability, that the only stable sampling equilibrium would be the strict Nash equilibrium. And the intuition for that was coming from evolutionary game theory, actually. Because in evolutionary game dynamics, replicated dynamics, or evolutionary game dynamics, strict Nash equilibria are always stable. Always stable, and any trajectories that converge to a rest point converge to a Nash equilibrium. All right? So that was my conjecture, and I made that conjecture when Rubinstein presented this paper in the Columbia Theory Seminar. And he very politely said, I don't know, I have not tested it, why don't you go and try and take a look, right? And so you write down its sampling dynamics. In fact, the easiest, simplest sampling dynamics is just this. The rate of change of Pi should be the likelihood that it wins the sampling minus the likelihood with which it is currently being played, right? Anything linear will work. It'll keep the unit simplex invariant. So anything like this will work. And we define a stable sampling equilibrium as a stable rest point to the sampling dynamics, okay? Now if you apply this concept and look for stability in that simple game, which of the sampling equilibrium is stable? This is what I found. No matter how close you start to the strict Nash equilibrium, probability almost 1 on low, almost 0 on the other two actions, your trajectories under those dynamics will converge to the interior sampling equilibrium, which is putting weight on dominated strategies. So not only are you getting a non-Nash prediction, there are positive probability with which dominated actions are played. And this is not because you care about the other person's payoffs or, it is coming because of the procedure you're using in order to choose actions. So sampling equilibrium is not just reproducing Nash equilibrium. In fact, it's doing quite the opposite. So although strict Nash equilibrium must be sampling, in this particular case, it is an unstable Nash equilibrium. The Nash equilibrium is unstable, and the non-Nash strategy is actually stable in this case. So very quickly, I'm just going to give you one theorem from a paper that was published quite a long time ago now in Games in Economic Behavior, which tried to say, well, what is it about this game? What is going on? What is it about this game? Can I identify sufficient conditions for instability of Nash equilibrium in a game like this? There must be some general conditions under which you get instability. And the condition is something called inferiority. So let me just quickly give you that, then I'll stop, and then we'll continue tomorrow. So if you take an action profile in a symmetric game, right, which we call AQ, we'll say that the action profile is inferior if for every player I, for every action I, there exists some other action different from Q. Wait a second. Sorry, for every player I. Okay, let me just say this in words. An action is inferior. So take this action profile, LL. An action profile is inferior if for every deviation by the other player, from L to M or L to H, there should exist a deviation for me, right, such that I, forget about the other player, I am better off than I was at the incumbent state. So you can see that inferiority is satisfied here. If this person deviates to M and I deviate to M, I will be better off than I was originally. If they deviate to H and I deviate to M, I will be better off than I was originally, right? So it satisfies inferiority. Now, if for every deviation, there are two different ways for me to be better off, two different deviations from me that leave me better off than I was at the original state, then I say that this original action profile satisfies twice inferiority, okay? And the result says that if your Nash equilibrium if your Nash equilibrium, if you have got more than 3 players, if you've got 3 or more players, inferiority is sufficient for instability. You will get instability as long as the Nash equilibrium satisfies inferiority. If you have a 2-player game, then you need twice inferiority. And you saw that in that example, you get, so the sufficient condition is satisfied. So it's not just a simulation that I showed you. The simulation just illustrates a deeper result. Okay? So where I want to stop, so I'm going to continue tomorrow. But the last thing I want to say before I stop is that what we have here is a solution concept that is different from Nash, that encompasses Nash in a sense because strict Nash equilibria are sampling equilibria. But once you refine the solution concept by using stability, you actually knock out the Nash in some games and you end up with something that is very different from the Nash prediction. Once you have that, you can then go look at the data and try to see which of these 2 solution concepts best fits the data. And so tomorrow when I start, I'll do that with a couple of examples with common pool resource games and public goods games. And then I'll talk about the most recent work, which is unpublished right now, which is on repeated games, sampling equilibrium in repeated games. But I'll stop there for today. Do we have time for questions? No.
We have a couple of minutes actually, and then we can continue afterwards.
Yeah, sure. Yeah.
So, 2 questions.
Yeah.
How to extend this concept with continuous strategy? Because, continuous set. Is it like you take the gradient and you put some noise or?
No, I wouldn't do it that way. The way that I would do it, so there's some recent work by Bill Sandholm that looks at slightly different sampling procedures. The way with continuous strategies, that's a very good question actually, because you can't sample the continuum. Almost by definition, you're forced to choose some finite sample, right? Otherwise it becomes. So instead of using a gradient and so on and so forth, my preferred approach to doing that, I've not done it, but my preferred approach to doing that would be that you have an incumbent action and you pick some subset of actions from the continuum and you sample against those. So, and you have a positive probability of selecting, from any interval in the continuum. So, for example, in the half the average game, so if you think about half the average game, there's a continuum. Imagine that there's an incumbent action that you're taking and you're called upon to update and you want to sample. You will sample some subset of other actions from the continuum such that every interval of actions has positive probability. That's the way I would do that. That's similar to something that Sandholm has proposed even for finite games. Even for finite games, if you have a large number of actions, you may want to sample only some subset of them.
But then, it's going against the literature of bandit or all these things where when you have a continuous of action, you try to approximate the gradient, because what you are doing is more or less kind of bandit, as you said.
Yeah, but you're right that once you get to continuum, I don't think it makes sense. I don't think it makes sense to continue along those. It was an analogy, and I don't think it works for the continuum. For the continuum, to me, what makes sense is that you sample in the continuum. Oh. You don't sample the continuum. Oh. Yeah, you can't sample the continuum, of course. Yeah.
And the other question is about assuming that you really want to do a statistical analysis of your data using this equilibrium. So, game theory, I'm okay.
Yeah.
Statistics, I'm okay. But assuming that doing the bridge between the two is really hard, especially if you have multiple equilibrium and so on, So how can you ensure that your data is consistent with this equilibrium? So I don't see a clear statistical test or so on to say, okay, it's coming from this game with some probability and p-value, whatever.
Yeah. All I can show you tomorrow is mean squared errors. I can show you. Yeah.
But how you select an equilibrium?
Oh, the games that we have looked at empirically have a unique. They have multiple equilibria, but only a unique stable sampling equilibria. So the stability is very powerful refinement in this case.
But if you have multiple.
Yes, certainly there are games, for example, certain coordination games where you will have multiple stable sampling equilibria. In that case, I don't know. I mean, how would you test empirically? Those games may not provide a good test of sampling equilibrium relative to quantal response, or you have the same problem with quantal response, but
no, even
with Nash equilibrium, I don't think that those games will provide a way of having a clean test of sampling versus others. I don't think so. At least I don't see how. certainly with the case of, in the case in which you can knock out all but one equilibria through the refinement of stability, there I will show you some results tomorrow.
So yes, this is what I'm saying. If you have unicity,
Yeah.
it will work well.
Yeah, yeah.
I'm sure of that.
Yeah.
Right? But I think what is interesting in game is like you have this fixed point that have multiple solution and
Yeah.
perhaps.
Yeah, I don't think, but yeah, I don't see how you would deal with that, but then that's common to every solution concept, right?
Exactly.
Yeah.
No, it's not depending.
Yeah.
Let's break for discussion, and we'll be back at 11:15 for Elena's talk.